Thank you very much for the introduction and for inviting me to talk here today. We'll move on into this then. Every scientific discovery is an incremental construction that's built on previous work, using ideas and data that's accumulated often over very long periods of time. So in a completely different realm from geological exploration, the recent discovery of the Higgs boson wasn't achieved in isolation, in a sudden leap of brilliance, but through a long train of scientific progress. It could be dated and traced all the way back through Sir Isaac Newton and beyond. The scientific method is based on the recognition of a testable problem, and then the formulation, testing, and modification of hypotheses. This process is accompanied by throughout the process, through the systematic acquisition of data, either through observation, things like mapping, or through experiment, essentially geophysical type surveys, etc. The role of geophysics is to constructively add to this process of systematic data acquisition, and using this to then iteratively support the formulation and testing of hypotheses, or in this case, geological interpretations. Geophysics is one of several tools that is available to the explorationist to help in this process of scientific discovery. And these tools are basically used to de-risk the exploration process, i.e. reduce the cost and increase the likelihood of a successful outcome. The changing role of geophysics really is really related to its application. If you go back far enough, geophysical surveys were tended to be used to look at very shallow problems, shallow investigation of the subsurface, and generally fairly small, well-defined survey areas, whereas now they tend to be used to explore to much greater depths. In the mineral exploration business, it's typical to be looking to 500,000 meters depth, and in much larger survey areas, so areas of several tens of square kilometers. And it's not uncommon indeed to actually find surveys which are extending these by maybe 2 orders of magnitude. So the changing role of geophysics has been accompanied and achieved, really, through the improved scientific understanding of the physical principles that are at play here, and also through technological advances, and perhaps particularly with technological advances. If you look on the left-hand side, there's a pseudo-section of some IP data acquired probably back in the early 1970s, lifted from Telford. Shows 4 N levels of data. Probably quite a simplistic and simple processing of the data set, and a very simple method of displaying this data, and also a very qualitative interpretation with an IP anomaly marked in the middle of the section. This compares a little bit to the more sophisticated data processing that leads to these kind of broadband tensor magnetotelluric results on the right-hand side, which are then displayed and modeled in with quite complex and computer-intensive algorithms. Technological advances in instrumentation have led to much higher resolution instruments, much higher resolution receiver systems with more digital bits of resolution in their analog to digital converters, and also less system noise. It's also led to more distributed array designs, which provide more autonomy and flexibility for the efficient acquisition of data. It's not just enough to acquire good data, we also need to do it in an efficient manner. And we've also seen technological advances in data processing. It's becoming more and more common for geophysical data acquisition systems to acquire full time series data recordings, which, although is very storage intensive, provides an enormous level of flexibility in terms of being able to process the data, post-process the data in more sophisticated manners, and also to be able to go back and reprocess data from what's really truly raw data rather than some sort of half-processed information. So as with the advent of a new idea or methodology and how to extract more and better quality information from a particular data set, having that time series data does allow you to go back and do that. Computer advances have also allowed us to now carry out mathematical processes on data that even until quite recently was simply impractical, would take too long. We can look at induced polarization perhaps in a little more detail to try and understand and look at some of these particular advances and how they've affected the role of these types of methods in the exploration process. I've chosen induced polarization, partly because it's what I'm perhaps almost most comfortable with, but also because it is much used in the exploration in Chile and through Peru, etc., given its very high sensitivity to the presence of disseminated sulfide mineralization. The similar story can also be told for most other geophysical methods, magnetotellurics, transient electromagnetic, seismics, airborne methods, etc. Essentially, if we look at IP especially, the aim has been to be able to investigate larger depths and to provide more efficient coverage of larger survey areas, or conversely, perhaps providing more detail in any particular given survey area. The approaches to achieving these aims is basically to improve the signal-to-noise ratios, allowing us to look to greater depths, and logistical improvements to make these surveys more efficient. Looking at the second item here, the logistical improvements, for a given survey type, really the efficiency, certainly you can use novel array designs, vector IP designs, or hybrid type array styles, but for any given survey array, the efficiency really is about maximizing the proportion of the time when you're acquiring data and minimizing the amount of time that you spend in installing the instrumentation and then picking it up. Distributed array systems go quite a long way towards this, especially if you're using these very sort of dense acquisition schedules where, for example, IP data is acquired throughout the daytime period, and then the nighttime period when you really can't acquire IP data for primarily safety reasons, you could acquire MT data, which doesn't require a transmitted signal. So, for example, the pseudo-sections that are shown here come from a line that's just a little bit over 5 kilometers long. It's acquiring their pole-dipole data, acquired with 200-meter dipoles, down to N levels of about 20 or 25. And the data was acquired by populating the entire 5-kilometer line with receivers and then simply stepping along through that line, transmitting, injecting current to be able to build up this information, this data set. Then during the nighttime periods between days of acquisition, magnetotelluric data could be acquired. Improving signal-to-noise ratios in IP basically has to do with a simple equation that signal-to-noise is simply the signal divided by the noise. So we can either increase the signal, essentially for IP this revolves around transmitting more current, or increasing the distance between the electrodes which are measuring the electric field. Both of these actually have some pros and cons to them. Transmitting more current may require more time-consuming, costly preparation of electrode contacts, or perhaps a less portable transmitter system. Whereas increasing the distance between electrodes can actually lead to larger amounts of electromagnetic coupling in the data, which is a kind of systematic noise that arises in IP data, and also would obviously also reduce the resolution of the survey. Alternative, or ideally actually something that you then also do, is to decrease the noise in the signal. This can be done through using receiver systems that have more bits of resolution in them, improving the quality of the electrodes and their contacts with the earth, improving filtering techniques. Stacking and averaging is a filtering technique that has essentially always been applied. It has a disadvantage to get a long stack of data. You have to acquire data for a long period of time. Time and frequency domain filtering also provide very powerful ways of removing parts of the spectra of the total measured signal, which are considered as noise. Recently we found that thresholded wavelet denoising can provide a very powerful alternative to the usual fast Fourier transforms and frequency domain filtering. There are also predictive or inferred noise cancellation techniques for IP. Telluric cancellation is becoming more common and more typically used. And we can also look at monitoring and deconvolving or removing noise that's generated within the actual acquisition system itself. So monitoring the current, transmitted currents aren't perfect, monitoring and then removing the effects of the noise that are being generated there can also assist. The idea is essentially to move from data that looks like that on the bottom left-hand side of the picture on the screen, where we've got a nice strong signal, very low levels of noise, and a very clean-looking result, which would provide a good quality piece of data for this scientific discovery process at the end of the day. And we really don't want to be acquiring data that's also ours, that's on the lower right-hand side, which shows a very small signal and high levels of noise, and really some information that's essentially useless. Well, the aim of all of this preamble on signal-to-noise ratios is basically to be able to look to ever greater depths. In the lower part of the slide, you can see a pseudo-section of, I think it was 100-meter pole-dipole, bidirectional pole-dipole IP data. Here are the chargeability parameters being plotted. And it's extending down to n levels of 25. N levels basically refer to how far apart the transmitter and the receiver were for at any particular moment. A very clear chargeability anomaly. You probably can't make out the numbers, but the reds, the warm colors at the bottom of that pseudo-section are getting up towards 30 millisecond or so response, quite a significant IP value. Modeling that provides anomalies that would be seated down at depths of probably about 5 times the dipole length, so in this case about 500 or 600 meters. If we were to throw away all of the data on the deeper of those n levels and acquire only n levels 1 to 6, as was perhaps more classically done, certainly in decades past, we'd end up with the pseudo-section that looks like the one at the top of this graphic, where there's really very little evidence of this deep chargeable response and anomaly. So, and a fair likelihood in that case then of actually missing out on the existence of this deep sourced anomaly. So moving on to a case history and trying to look at an example where we've both acquired some quite efficiently some broad coverage data set and also a more detailed deep imaging data set. I'd like to revisit this Atlantida case history. Atlantida is a buried copper-gold moly porphyry in the third region of Chile, about 60 kilometers to the northeast of Copiapó. And according to a paper by Steve Anderson and Matthew Hope, the early exploration was focused on nearby outcropping skarn, with an IP survey that was done pretty much concurrently, defining a large chargeability anomaly beneath cover, but which drilling didn't actually test. INMET in 2010 through to 2012 carried out further geophysical surveys and drilling, primarily based on this IP anomaly, leading to the discovery of the Atlantida porphyry system. The surveys that I'm going to show now, or the results of surveys that I'm going to show now, were actually carried out more recently as test surveys to try and characterize the signature of this porphyry. They involved about 54 stations on a 1 by 1 kilometer grid shown there with the white dots covering the survey area, and those were red with vector IP and magnetotellurics. The transmitters for the vector IP are marked in green. And then the red line was a single 5.2 kilometer line of 200 meter pole-dipole IP, also red with magnetotellurics. Looking first at the results of this pole-dipole IP line, it was acquired, the pseudo-sections I showed before were actually for these lines, so it was acquired down to n levels of about 25 and provided a model that is probably reasonably well resolved down to depths of certainly 700, perhaps closing towards kilometer depth. In the upper part of this graphic, you can see the results of 2D inversion for resistivity, and then the lower, the 2D inversion for chargeability. In red is an isosurface taken from a voxel of the copper grades from drill holes. The sort of semi-transparent red color is 0.05%, and there's a solid red inside of that, which actually includes a large part of it, which is 0.1% copper. A very good correlation was seen here to the lowish resistivity. It's not tremendously low resistivity, about 300 ohm meters, but there's a clear anomaly, discrete low resistivity anomaly that lies beneath the shallower cover response that can be seen in the upper part of that model section. And in the case of the IP, there was a clear chargeability anomaly very, very large values, rising up above 50 milliseconds, which certainly encompasses the mineralization and also extends out further. It's likely that a large part of that anomaly really relates to the presence of pyrite within the system, although certainly the copper sulfides wouldn't hurt. Makes the anomaly significantly more extensive, larger, which could be difficult and complicate life in the exploration scenario, but is actually in some ways beneficial and allows a larger footprint to be able to discover these things in the first place. Magnetotelluric data was also acquired with contiguous E-fields, often referred to as EMAP-style magnetotellurics, on the same line, and also provided a very clear, discrete conductive anomaly. Vector IP data acquired on this 1 by 1 kilometer grid of stations showed again in the top left a very clear low resistivity anomaly, and in the bottom right a nice strong chargeability anomaly, well focused on the surface projection, which you can see in a sort of semi-transparent white color there of the ore shell. 1 by 1 kilometer grid of tensor MT data modeled just in one dimension and stitched together showed this very clear orange-colored zone of low resistivity. It was the only one within that 54 square kilometers of this nature, which shows again a very good correlation to, in the top left, the copper, the elevated copper in the drilling, and in the bottom right, the elevated gold. That's an isosurface cut at 0.1 grams per ton. There's a slight difference between the locations of all of these features, but really you can't expect too much from a 1 kilometer space set of survey measurements either. And interestingly, following a lead by Steve Boucher, a three-dimensional inversion model was also carried out on the vector IP data. It's not normal to do this. Vector IP data is usually not considered adequate for this kind of process, but in this case provided a shell shown here in magenta over again copper and gold at 30 millisecond response, and very neatly contains these anomalous responses. In fact, actually also shows a dip heading off towards the southeast, which has some geological significance too, I believe. Does this make geophysics a silver bullet? Certainly not. Geophysics should only just be treated as an integral part of the exploration process. And that process does have to be considered as an iterative process where we're testing and modifying geological interpretations, hypotheses as we go. And there certainly is never a single unique solution to any geophysical modeling. So the first model is not necessarily the best model. There's also limitations to geophysical techniques which have to be considered and must be borne in mind when we look at these things. As we move towards some of the challenges in geophysics in its future role, the largest one is clearly just to be able to actually know what its future role will be. There's a possibility that maybe in-mine or near-mine exploration will become increasingly important for geophysics, and it does present very specific challenges which we're not accustomed to, so perhaps in the more greenfield use of geophysics with very high levels of cultural interference, electromagnetic noise, difficult logistical problems, etc. We also need to focus on increasing the efficiency of geophysics, especially ground geophysics, which continues to be very labor intensive. Wires need to be pulled out, holes dug, etc. Airborne platforms, even drones, perhaps are interesting ways to look at improving the efficiency of some of these methods as we move towards the future. We need to worry about the development of the next generation of instrumentation and the education so we have a continuance of experienced and well-versed professionals in the industry. And last but certainly not least, we need to concentrate and look at maintaining the continual improvement in health, safety, environment, and the community relations that all revolves around the work of geophysics within the exploration process. There's been some moves in recent years with the Ground Geophysical Safety Survey Safety Association, essentially out of Australia, in this line, specifically looking at trying to instill best practice in this area for geophysics, and I think those things really deserve our support. The role of geophysics, I think, is likely to play a part in achieving the next great discovery in Chile. And according to this is going to happen basically by the systematic acquisition of data and then working through this in an iterative manner without falling into a science project, has been pointed out before, but to test and formulate geological interpretations. I think perhaps the most important thing here, though, is really the ability to be able to build on and improve on past ideas and data sets. That's really going to be fundamental to the exploration process. Thank you.